All right, welcome back to calculus. I'm going to continue on with continuity. In case you're wondering why the first video was so short, I ran out of markers and had to find some more. So here we go. Theorem 8, some properties of continuous functions. So basically we're going to do for continuity what we did for limits. Remember we had all those limit laws and we said, hey, if you can find the limit of f and you can find the limit of g, you can add them, you can subtract them, and all those kinds of things. Turns out continuity works the same way. And we really shouldn't be terribly surprised because, continuity is defined to have that the limit is equal to the function value. So, if the limit exists, then it's going to follow all the rules for limits. And if the function value exists, if the limit is equal to the function value, then you're basically there. So properties of f and g are continuous at x equals c, and k is a constant. The following are all continuous. Sums and differences, so f plus g or f minus g, I didn't write that one down. Products, f times g. Constant multiples, k times f. Quotients, f over g, just so long as the function on the bottom is not actually equal to 0, that would be bad. Powers and roots. Now with powers and roots, n here has to be a positive integer. Okay, weird things happen if n is something else. So at this point, we're just going to leave them as positive integers. And with roots, we have one more little potential hiccup. F has to be defined on an open interval containing c. So here's what I mean. Here's a graph of square root of x. It's just a rough sketch, but here's what we can see. Let's look at c equals 0. As c equals 0, we're looking at this point right here, and we want to know if it has continuity there. Well, it doesn't, right? It has one-sided continuity. It would be right continuous at c equals 0, but it's not going to be continuous at c equals 0 because there's nothing over here on the left. So we can't find an open interval around there where the function is defined. Okay, any open interval we try to put around c equals 0 is, half of it's going to be undefined. And so you can't have continuity there. Certainly we have right continuity, but we don't have full continuity. So there we go. Let's keep going. Let's look at inverses are next. All right, here are a few more things that are continuous. This is not an exhaustive list. So that's part of what makes all this so fun. There's so much stuff. Inverses of continuous functions are continuous. And really that's just because all an inverse is that it's a reflection over the line y is equal to x. And so again, if you go back to our basic idea of continuity as being a graph that you can draw without picking up your pencil, reflecting it over a line is not going to change the fact that you can still draw it without picking up your pencil. Composites are continuous. So if you have f and g are both continuous functions, then if you composite them, then they will still be continuous functions. And it turns out trig functions are continuous on their domain. Now that's important because let's talk about tangent for just a second. Tangent has a bunch of vertical asymptotes, right? The first ones that come to my mind anyway are negative pi over 2 and positive pi over 2. You can certainly graph it on your calculator or go back and look over tangent and see its graph. Anyway, it's got vertical asymptotes. But the important thing is that negative pi over 2 and positive pi over 2 are not in the domain of tangent. So in between those, which is, in between negative pi over 2 and positive pi over 2, that is the domain of tangent. And so in between, tangent is continuous. And so all the trig functions are continuous on their domains. So let's look at an example. All right, so here's an example. We want to show that the function f of x equal to the absolute value of x times the sine of x, all divided by x squared plus 2, is continuous. Now, that looks like a mess. And let's face it. Okay, I'm not going to lie. It is a mess, right? This is a nasty looking function. It's got a trig function tucked on inside of an absolute value. It's got multiplication of stuff. It's got powers. It's got a quotient. This is a big mess. But here's the thing. It's really not that bad. Let's take a look at it. Let's take a look at why it's not that bad. First, ignore the absolute value. Everything inside, all of those different pieces inside, and this is my absolute value, all those different pieces inside the absolute value are each continuous. X by itself is continuous. Sine of x is a continuous function. X squared, the 2, all of those are continuous functions. And so by theorem 8, that theorem we just looked at a minute ago, the entire inside of that is continuous, right? We have products and sums and powers, and we know that all of those things are continuous. So we don't really have to do any crazy work here. We don't have to try and evaluate a limit and show that it's equal to what the function is. No, we're good. So next, we just need to worry about this absolute value. And it's really not terribly hard. I'm going to leave you to try and figure it out. It shouldn't take you very long. It's entirely possible to show that the limit as x approaches c of the absolute value of x is equal to c. Kind of makes sense, right? Or I'm sorry, is equal to the absolute value of c. Kind of makes sense. That's how absolute value works. And it's going to be that way for any function. And this is our definition, right? This is our definition of continuous. If this limit exists and is equal to the function, when you plug in the number, that's what it means to be continuous. And so once we have that the absolute value part is continuous, then what we have is a composition of continuous functions, right? We have the outside function of the absolute value, and into it we have plugged in this big nasty mess, but basically it's all continuous. So there we go. Let's move on. More fun. All right, we're starting to get a little bit closer to being done. A couple more boards and it'll all be taken care of. Theorem 10, if G I'll try that again. If G is continuous at B, and the limit as x approaches c of f of x is equal to b, then the limit as x approaches c of g of f of x, so here we have a composition function, is equal to g of b, right? And then remember where b is that limit of f of x, and that's equal to g of the limit as x approaches c of f of x. And so that's kind of a weird little theorem. Basically, it says you can bring a limit inside of a composition function. And that's nice because we have weird looking examples like this one. Let me move to this side, that'll probably be better. So what we're going to do, what we have here is we have this big nasty limit. And the first thing I want to point out is it really is in two parts. This square root of x plus 1 is almost just extra to what we're really looking at here. We have multiplication. We know a lot of stuff about the limit of the square root of x plus 1. Basically, we just have to plug in 0, right? Because if we ignore this e to the tangent x, we know that the square root function, the limit exists everywhere that the function is defined. And so we can plug in 0 here just fine. It's not a big deal. And if you follow it down, that turns into a 1. Right, you just plug in the 0 and hey, we're happy. Now, the e to the tangent x, that's a mess. Right, we haven't done that limit, and we're not even entirely positive how we would do that limit. But we can take advantage of this that we had here, because e to the tangent x is a composition function. It's an exponential function, e to the x, where we've inserted a tangent into the inside. Now, the important thing here is that e to any power exists, right? E is defined for all real numbers, so anything that could possibly come out of a tangent, e to that power works. And so it fits the criteria that we have here for this theorem. So basically what we're going to be allowed to do is, instead of having the limit on the outside, instead of trying to take the limit of the e to the tangent, we can do e and then just do the limit of the tangent, and that's pretty straightforward. And so because here's the thing, once we pull that limit inside, for tangent it's a trig function, and we said that those were all continuous, which means that the limit exists, and the limit is equal to what you get if you plug in the number, in this case 0. Right? We love continuous functions because we can just plug in the 0, or in this case 0. Well, tangent of 0 is 0, so we end up with 1 from the first part of the limit times e to the 0, and anything to the 0 is 1, so 1 times 1 just gives us 1. All right, let's keep going. All right, we have 2 more boards, counting this one. Almost done. The intermediate value theorem. The intermediate value theorem says if f is continuous on a closed interval ab, so it includes the endpoints. And if y sub 0 is any value between f of a and f of b, then y sub 0 is equal to f of c for some c in the interval. So here's what that means. Here's a picture. Here's my interval from a to b. You can see I drew a graph. So I have a function value of a and a function value of b that I've labeled on the y-axis. And in between, I've picked any y sub 0. Okay? Because that's the setup here. Y sub 0 has to be between those two function values for the endpoints. So what it says is that there has to be a c down here that's in between a and b that will give you that value. And basically, I think this makes sense. We have a continuous function, which means you can't pick up your pencil, which means somehow you have to get from here, f of a, to up here at f of b, and you're going to have to go through this y sub 0. Okay, so there's going to have to be some value in between a and b that will pop out that number, because otherwise it wouldn't be a continuous function. Otherwise you'd have a jump or a hole or something, and it wouldn't work. Okay, so we have one more thing we want to do. On the next board, we're going to look at removing a discontinuity for the removable case. And so this is actually pretty straightforward, and we'll see what it looks like here just as soon as I change the board. All right, so here we go. My last example, the removable discontinuity case. So the removable case, if you're picturing a graph in your head, this kind of graph has just a little hole in it. And that's what's going to make it removable. Basically, you could take your pencil and you could fill in that hole, and then it would be a continuous function. So let's take a look at an example that has a removable discontinuity, and then we'll get rid of it. Show that f of x equal to x squared minus x minus 20 all over x squared minus 4x minus 5 has a continuous extension at x equal 5, and find the extension. So first of all, it's worth noting that 5 is a problem here. If you plug it in, 5 squared is 25, 4 times 5 is 20, so 25 minus 20 minus 5 is 0. You get 0 in the denominator. That's that means that certainly we don't have a continuous function here at x equal 5. Now, this is a rational function, so it's going to be continuous most places, but it's not at 5. So let's see if we can get rid of that discontinuity. Remember, what we need to have it be continuous at 5 is the limit needs to exist, and the function needs to equal that limit. So let's work with the limit. Let's see if we can find the limit as x approaches 5 for this function. Well, a little bit of factoring will get us that the limit as x approaches 5 of x minus 5 times x plus 4 over x minus 5 times x plus 1. And here's where we can see that it's going to be removable. We know 5 is a problem, but now we can see that those x minus 5s are going to drop out. They drop out, and so we're left with the limit as x approaches 5 of x plus 4 over x plus 1. And now 5 is not a problem, right? We can plug 5 into this, and so we're going to go ahead and do that. We plug it in, 5 plus 4 is 9, 5 plus 1 is 6, we get 3 halves. So the limit exists, right? The limit of this function as x goes to 5, it exists. And so all we need is to define the function as so. We define it as a piecewise function. F of x is equal to that big mess that we started with as long as x is not 5. And then we define it to be 3 halves at x equals 5. So we have plugged the hole. We gave it the value that we found that its limit had. And so if you have, it's usually going to be rational functions, but there are probably some others. If you have a function and you can show that that the limit does exist, even though the function doesn't work there, you can plug the hole. And that's what we did. So thanks for coming and have a good day.